Fine. So basically we will be discussing the formal theory of shell model. Right. Now before I jump to the topic of shell model, let me have some discussion, very general type of discussion. So what is this shell model? What does it describe? So basically it describes your atomic nucleus. Right. Okay. Good. So basically we want to study the structure of the atomic nucleus. Now what is this nucleus? Well, as you know, this is basically a many-body quantum system, this atomic nucleus, having protons and neutrons, right? Now, in this regard, now there are many body quantum systems. Now, out of them, this atomic nucleus is particularly unique. You know why? It is unique in the sense that it consists of two types of fermions, two types, right? Protons and neutrons. Also, another point is that there are finite number of constituents, inside this nucleus. Now, when I say finite, what I mean to say is that the number of nucleons, it is too few. So, it is too few to be treated statistically. বুঝতে পারছো? Or not to be too few? Tell me. Basically, what I want to say is that, you see, the number of nuclei, what is it? Say 1 to roughly 300, right? Now, what I want to say is not too few. Please pay proper attention. Okay, it is not too few, but instead it is not too few. So, what I want to say, it is not too few to be treated exactly. Right. Similarly, on the other hand, it is not too large to be treated statistically. Right. So this is what we have to deal with. So basically we have got a quite complex system to describe. Now, how do we proceed? Let's talk about some basics. Now, basically, you can talk about solving the many-body problem, where we start with the oversimplified form of a nuclear potential, right, such as a square wave or a harmonic oscillator, where we could in principle write down a set of coupled equations describing the mutual interaction of the nucleons. However, note that these equations cannot be solved analytically, but instead must be attacked using numerical methods. So this is one problem. Difficult, right? The second problem has to do with the nature of nuclear force itself. You see, there is evidence to suggest that the nucleons interact not only through mutual two-body forces, but three-body as well. So, two-body plus three-body as well. Right? Although this is much small. So, what I mean to say is that the force on a nucleon, say nucleon A, say small a nucleon, not only depends on the individual position of nucleons, say small b and small c, but also it contains an additional contribution that arises from the correlation of the positions of nucleons B and C. You understand what is this? This means that life is getting more and more complicated. And remember that we do not have a classical analog. for such a system. It does not exist. Now, in principle, you can say that, sir, we can do additional scattering experiments, right? For the three body systems, we can do scattering experiments to try, in analogy to the two body studies, to extract some parameters so that we can describe this three body force. However, upon doing so, we quickly reach a point at which such microscopic approach obscures rather than illuminates. There are too many technicalities, and we are unable to get the essential physics of the nucleus. And it is somewhat like trying to obtain a microscopic description of the properties of a gas by studying the interactions of the atoms and then trying to solve the dynamical equations that describe the interatomic forces. Okay, so most of the physical insight, you see, into the properties of a gas comes from a very few general parameters such as pressure and temperature, rather than from a detailed microscopic theory. So similarly, we are having same analogy here. So what do we do because of all these troubles? So what we do is we adopt a different approach. Of understanding the nucleus. And this is the approach of nuclear models. Okay, so what we do basically, we choose a deliberately oversimplified theory. But again, we choose one that is mathematical tractable and rich in physical insight. Now, if that theory is fairly successful in accounting for at least a few nuclear properties, then what can we say? We can say that let us try to improve it, right? By adding some additional terms. Now, through such operations, we can construct this nuclear model, which is basically a simplified view of the nuclear structure that still contains the essentials of the nuclear physics. Remember, the word essence, this is what we want. We want the essence of physics. We don't want the details of when one particular nucleon will be there, its position, its momentum, its energy. We don't want that. We want the observable properties to be explained in terms of microscopic physics, and that too in a way which gives us as much complicated things as possible. We want the essence, basic physics information. Okay. Now, it is important to remember that a model must satisfy. Anything cannot just be a model in itself. There are certain requirements. Okay. A model must satisfy basically two criteria. Okay. First one is that it must reasonably well account for previously measured nuclear properties. Okay. And what's next? The next has to do with the predictions. So, it must predict additional properties that can be measured in new experiments. Okay. Now, this system of modeling, so basically we are talking about modeling atomic nucleus, right? Now, this is not just a technique which is unique to nucleus. Such complex modeling is present in many other branches of science, say in atmospheric science and even genes. There also such modelings are there. Okay, so this is the basic idea. So we are following the route of nuclear models. Now, talking about nuclear models, you see there are two basic classes of nuclear models. One is collective model. This is the first class. And what happens here? Basically, in this class of models, here we assume that the nucleons interact strongly. So we assume that nucleons interact strongly in interior of nucleus, inside the nucleus, and mean free path is small. Now this is identical to that of molecules of a liquid, and the liquid drop model, here you see LDM, liquid drop model, belongs to this class. And here, using this collective model, we study phenomena that involves nucleus as a whole. Okay, what's the other class? You must have guessed, right? The other class belongs to, you see, independent particle models. Here, what we do is that we assume that Pauli's principle. Why Pauli's principle? Come on, we are talking about protons and neutrons, right? They are fermions, so of course they will follow Pauli's principle. So here we assume that the Pauli's principle, it restricts the collisions of the nucleons inside the nuclear matter, leading to a larger mean free path. Okay. Now the several forms of shell model belong to this class. Okay. You must understand that nucleus can exhibit both collective as well as independent particle phenomena, and you also have to understand that each model finds its usefulness in the explanation of a specific group of nuclear properties. This is what? Various forms of shell model. So this is what we will be talking about. Right. So we started with the difficulties of studying a quantum many body system. From there, after many discussions, various possibilities, various problems, so we followed the route of nuclear models. Now from the nuclear models, now we are talking about independent particle model, and there we are now talking about one of the models, which is the shell model, which is our topic of interest. So shell model. Okay, now you see this model admits that the nucleons move within the nucleus independently of each other. So here basically nucleons move independently of each other. Now where have we seen this previously? Now this is quite similar to that of Fermi gas model. There also we have the same concept. independent. However, there is a difference. The difference is that now the nucleons in shell model, the nucleons are not treated as free particles. So in Fermi gas model, the nucleons are treated as free particles, right? However, in shell model, here the nucleons, they are treated as if they are not free, but they are subject to a central potential. Okay. Similar to the central potential that acts on electrons in an atom. Now, at first sight, this idea is a bit strange because we cannot, as in the atomic case, identify the origin of such potential. However, you see, this difficulty is resolved by assuming that each nucleon moves in the average potential created by the other nucleon. So, something like this, each nucleon is basically moving in the because of the average potential of the other nucleons. Something like this. And that potential should be determined in a way to best reproduce the experimental results. Okay. Now, historically, you see, the first proposals of the model appeared at the end of around 1920s, motivated by fluctuations in the relative abundance and masses of nuclei along the periodic table. Now, you know these things. You have studied this in your graduation as well as MSc first year. I am not going to talk about the details of such. However, it is important to note that because of the lack of an apparent theoretical basis and the low acceptance of the idea of independent motion of nucleons, together with poor initial results, remember, I am talking about pre-L dot S interaction. So you remember, only after the presence of L dot S interaction can we really explain the experimental data. So this is prior to that era. Finally, when the L dot S or spin orbit interaction was introduced in 1949 by Maria Goeppert and Jensen, Meyer and Jensen, then it was established that shell model really can be used as an important tool in nuclear physics. Okay. So now with this, let us try to describe the shell model idea in a formal way. Okay. Now you see the exact Hamiltonian for a problem of, so basically we are talking about problem of a nuclei. So Hamiltonian, we can write it like this. One to A Ti Ri plus V R1 R2 R of A. Right, this is just basic idea. This is equation 1A. Here you see T is the kinetic energy operator and V is the potential function. Now, if we restrict ourselves, so restrict to two body interactions, that means nucleon-nucleon interactions, then we can write, you see, H is equal to summation over A, I is equal to 1 to A, here Ti Ri plus half of Vij Ri Rj. Okay, so you see the simplification from here. So this was the general potential. From there, because of the result of two body interaction, we are having this term. Now in the model proposed, the nucleon I, the ith nucleon, feels not the potential some Vij, but a central potential Uij. Okay, so not Vij but Uri, which is a central potential, right? Central potential. Why central? You see, just single coordinate. Okay, that depends only on the coordinate of the nucleon I. So I am talking about the ith nucleon. So we want that. So how do we do this? Let's do very simple mathematics. You see, this potential Ui, we can introduce this in a very simple way, like this here, you see. So let me again write H is equal to summation. So this is the Ti Ri term plus I am just adding this term, you see, Ui Ri plus the previous term, here also I, here also I. Here we have Vij Ri Rj minus your this term which has been added. Okay, now this is what we are doing. This time what I am doing is, let me call this term here, this last term, let me give it a separate name, which is H residual. Okay, so then what will we have? So we will have, because of this very simple mathematics manipulation, we will have H is equal to this summation Ti term plus summation Ui term, right? Or U term, basically not I. Remember, there is no I over here. This is central potential. So no I, and plus this residual interaction term. So let me do the nomenclature. So let this be equation 3 or 4, say 4. This one is 3. The previous equation here, this is equation 2. Okay, fine. Now here this H residual, this basically refers to residual interactions. What does this mean? This means part of, you see, that is, it is the part of potential not embraced by the central potential. So you see, the hope of shell model is that the contribution of H residual is small, or basically the shell model Hamiltonian is I is equal to 1 to A summation Ti Ri plus Uri. তোমরা এই জিনিসটা ভুল করবে না, দেখো এখানে কোনো সাবস্ট্রিক্ট নেই. This means this is a central potential, whereas this depends on the ith coordinate. Okay, so This is the shell model Hamiltonian. Now this represents a good approximation for the exact expression for H, only if H residual is small, right? Now later we will see that part of the lost accuracy when we pass from, you see, what is this equation number? This equation number is 5. We will see later on that part of the lost accuracy when we pass from equation 2. You see, what was equation 2? Basically equation 2 was just H equal to summation T plus half of summation Vi ij. So you will see that part of the lost accuracy, something is lost, of course, because we are considering that H residual is small. Now part of this lost accuracy can be recovered by an approximated treatment of the effect of residual interaction. It is possible. Okay, now we will see into that. Now you see the solutions. The solutions psi 1, R1, psi 2, R2 of the equation, say H is H0 psi equal to E psi. This is H0, and let me not write SM. This is H0. Okay. So you will see that, so the solutions this of the equation 0 psi 0. So this is what equation? Equation 5 chilo, eta equation 6 of this equation. Okay, with respective eigenvalues E1, E2, E3 and so on, they are known as orbits or orbitals. Now in the shell model prescription, A nucleons, they fill the orbitals, of lower energy in a way compatible with Pauli principle, right? Thus, if the sub-index 1 of psi 1, which represents the group of quantum numbers of the orbital 1, includes spin and isospin, we can say that the first nucleon is described by psi R1. Similarly, for 8th nucleon by psi A R A. Okay. Thus, the wave function psi equal to psi 1 R1, psi 2 R2, so on, psi A RA, right? এটা আগে আমরা করলাম here. Psi A RA is a solution of which equation? This equation, equation 6 is solution of 6 equation with eigenvalues E equal to E1 plus E2 plus En, Ea. Now, and it would be in principle the wave function of the nucleus with energy E given by the shell model. However, we should keep in mind that we are treating a fermion system, and so the total wave function should be antisymmetric for an exchange of coordinates of two nucleons. So this wave function is not applicable, and the proper wave function, taking into the fact of the antisymmetrization, is written in the form of Slater determinant. So let me write it down. So proper wave function, it is known as in the form of Slater determinant. Slater determinant. So it is written like this, factorial A, and here we have psi 1 R1, psi 1 R2, psi 1 RA, and here we have psi A R1, here psi A RA. Okay. হ্যাঁ বলো. Okay, so this is the Slater determinant. Now what about the equation number? We have to again write it down. So 6, this is 7, this is 8, this is 9, equation 9. Okay, note that here the change of coordinates or of the quantum numbers of two nucleon changes the sign of the determinant. Of course, we note these things. Now, you see this equation 9. Now, an inconvenience of the construction in equation 9 is that the function psi, by mixing well-defined angular momentum J and isospin T, is no longer an eigenfunction of these operators. Well, let me write it down. This is, now we are actually slowly moving towards how we really perform shell model calculations. So performing basically shell model calculations, how we do that. So I am just slowly and gradually moving towards this direction. So what I am saying is that the inconvenience in construction of equation, this one, is that the function psi here, by mixing well-defined angular momentum J and isospin T. So this is function J phi. So we mix J and T. Then after that, after we mix this, then this psi is no longer an eigenfunction of these operators. Now this is a problem. This is the problem. So of course there is a solution, otherwise people will not be doing the shell model calculations. So what's the solution? The solution to this difficulty, involves the construction of linear combinations of Slater determinants that are eigenfunctions of angular momentum J and isospin number T. Now this problem has a well-known solution, but it involves a great amount of calculation. A large computational power is required. It is important to make clear, however, that many of the properties of nuclear states can be extracted from the shell model without knowledge of the wave function, as we will see now. Okay. So we will analyze what is obtained when one starts from the potential UR, right, with well-known solutions. We start with UR with well-known solutions. Now let us initially examine the harmonic oscillator. So first choice, harmonic oscillator. Now, being a potential that always grows with distance, at first it would seem not to be adaptable to representation of the nuclear potential. Why? Because you see, the nuclear potential, it goes to zero when the nucleon is at large distance than the radius of the nucleus. So it is expected, however, that it is not very important when we analyze just the bound states of the nucleus. Now you see, the oscillator potential has the form VR equal to half m omega square r square. So again, what is the equation number? This is, I think, 10. Yes, equation number 10. Okay, where the frequency omega should be adapted to the mass number. So omega should be adapted to the mass number A. Now let us try to find solutions of this equation 10 of the type psi r is equal to ur divided by r y l m theta phi. Let us try solutions where the substitution of psi in the Schrodinger equation for a particle reduces the solution this to the solution. So upon putting this, what we will get, let me show you. So because of this, so putting in, we get this is not happening. Anyway, let me write it down then. So d2u dr square plus twice m by square e minus vr minus l into l plus 1 by r square, right, to u equal to 0. This is equation 11. We have done this type of problems many times, right? So the solution of this equation 11 with the potential of which potential? This potential, equation 10, right? So just let me write down. So this is equation 10, this one is 11, right? This one is 11 and this one is 12. So the solution of 12 for potential 11, for potential 10, let me write it down. Solution দেখতে পাচ্ছ তোমরা, this is equation 13. Now here this nu is equal to m omega h cross, and this v nu l is associated Laguerre polynomial. Now I'm not going to write the polynomial, where you see this thing you have seen previously. Now you see, so this nu n l r is basically l into nu r square, some form is there. Again, this follows in the solution. These are solutions of yet another equation, and that equation is this d2l. You don't have to remember these things also. I'm just talking about how people progress in doing the shell model calculations, but for that it is important to know the steps, and this is what we are doing. Again, from the normalization condition, which is basically UNL R dr equal to 1, we will obtain the values of NL. Okay, so this is about the wave function and all that. What about eigenvalues? You see, the eigenvalues, energy eigenvalues, corresponding to the wave function psi NLM are, it is given by E NL is equal to h cross omega twice n plus L minus half, and this we can write as h cross omega plus 3 by 2, or basically a new number. So here n is equal to 1, 2, 3, so on. L is equal to 0, 1, 2, so on, and this number is equal to 2n plus L minus 2. Okay, so now you see, for each value of L, for each L, there are twice into 2L plus 1 states with the same energy, or basically they are degenerate states. Now the factor 2 is due to spin states, right? To spin states. However, the eigenvalues that correspond to the same value of 2NL plus 1 are also degenerate. Now as 2n is equal to this minus L plus 2 is equal to even, so a given value of this lambda, it corresponds to degenerate states, eigenstates, having the value, you see, NL is equal to the plus 2 divided by 2, 0, next, sorry, 2, then 2 delta minus 2, 1, this. Okay, this is what, and this is for delta even, and we also have NL equal to the plus 1 by 2, 1, three, and so on, and last we have 2 delta minus 2, 1, and for delta odd. Now we obtain then that the neutron and proton numbers with eigenvalues E lambda are given by these values, you see. For even and for odd. Okay. Now note that in both cases the result is, what's the result? In both cases the result is that finally if you do the sum we will get delta plus 1 into plus 2. Now this quantum number basically defines a shell, and each shell it can accommodate Na or n delta protons and n delta neutrons. Okay, so the accumulated number of particles for all levels up to A is now this, if you do the sum you will get, this is delta plus 1 plus 2 and delta plus 3. Okay. Now based on these results it is possible to make an estimate of the frequency omega of the harmonic oscillator applied to a nucleus with atomic number A. You see, for a harmonic oscillator the expectation value of the kinetic energy of a given state is equal to the expectation value of the potential energy, right? We know that. Thus the sum of the energies of the occupied states in a nucleus of mass A, what is it? It is given by E is equal to m omega square A average value of R square, right? Now we can estimate this R square using this, where what is the value of R? The value of R is approximately 1.2 a to the power 1/3, right? Now let us assume n is equal to z and that all states up to energy A. So assume n is equal to z and all states up to energy E delta are occupied. Okay, then we will have A is equal to summation delta is equal to 0 to delta 0 twice of n delta, and this is equal to 2/3 delta 0 plus 1 delta 0 plus 2 and delta 0 plus 3, and this gives us approximately twice third delta 0 plus 2 to the power whole square plus terms of order delta 0, right? Now we are very soon near the end of our lecture, and also we will have this E by h cross omega is equal to summation delta is equal to 0 to the 0 twice n delta plus 3/2. This is again approximately equal to half of delta 0 plus 2, okay, to the power 4 minus 1/3 delta 0 plus 2. Now eliminating delta 0 plus 2, from equations above and keeping terms of larger order in delta 0 plus 2, then upon doing that you will see that we will get this result. I would like you to check this yourself. 3 by 2. What is the power? I would like you to find it by yourself. This will be your homework for today. Okay. And finally, using these above relations, we can show that this is the result. Again, what is the power? I will ask you to check this yourself and tell me in the next class. So this will be your homework. Okay, any questions? হ্যাঁ একটু পড়বে তোমরা এই জিনিসটা
হ্যাঁ স্যার
অনেকদিন পড়া ছাড়া হয়ে যেতে পারে আমি বেসিক্যালি জাস্ট হারমোনিক অসিলেটর ফ্রিকোয়েন্সি ডিটারমিনেশনই করেছি ইউজিং এ ডিফারেন্ট সেট অফ সিম্বলস ওকে অন অল দ্যাট ঠিক আছে ভালো করে পড়ো নেক্সট ক্লাসে দেখা হবে ওকে